We continue now with another mathematics program, and it's for the second level course, Introduction to Pure Mathematics. It's the fifth program on analysis, and it deals with differentiation.
Back in Unit 2, a flow is described by a set of slopes, one slope at each point of the plane. And flow lines were described as curves, whose tangent lines at each point were in the direction of the flow at that point. But in the previous section of this unit, we returned to these two ideas, and we reinterpreted them. Firstly, the idea of a flow was refined into the idea of a vector field. That is, the idea was augmented to include a magnitude as well as a direction at each point. So, at each point xy, we base a vector v of xy. And for the flow lines, each flow line was reinterpreted as the path of a function alpha from R to R2. That is, each point of the flow line is thought of as the image of a point T. This reinterpretation makes two notions of Unit 2 more explicit: movement and velocity. The notion of movement along a flow line is made explicit by thinking of t as time. So, as time t passes, the image of t moves along the flow line, and the velocity of the flow through each point of the plane is specified by the vector based at that point. So, that was how we reinterpreted flows and flow lines in the previous section. A flow became a vector field of velocity vectors, and for simplicity, we'll call that a flow field. And a flow line, that just became the path of a function alpha, which we call a flow function. Well, one particular example of that is defined like this. Here, the vector at a point xy has components 1 and y, and we write this as a column vector in order to indicate that it's a free vector and to distinguish it from the position vector, which we write horizontally. Well, in a moment we'll be looking at the flow lines for this, but first of all, we've got to consolidate our general theory. You see, at the moment it's incomplete, because we haven't got an explicit connection between v and alpha, and we're certainly going to need one, because they give us two alternative descriptions of velocity along the flow line. And we're certainly going to need these two descriptions to coincide. Well, on the one hand, we've seen that the velocities are specified directly by the flow field v. At each point alpha t of the flow line, which has coordinates f of t and g of t, say, the field v specifies a unique velocity vector. We can call it v of alpha t for short. On the other hand, we get an alternative notion of velocity from the function alpha, because of the movement defined by alpha. So, to clinch the connection, we need an explicit formula in terms of alpha for the velocity, and this has to equal v of alpha t. To get an explicit formula, we take a second point on the flow line at time t prime, and we consider the average velocity between the 2 points. That is, we consider the free vector based at alpha t given by this expression. Let me explain that. If we think of alpha t prime as a position vector and alpha t as a position vector, then their difference is a free vector from here to here. And if we divide by the time interval t prime minus t, we get another free vector in the same direction, but with a different length. And in fact, it's exactly the velocity you would need if you wanted to travel from here uniformly along this straight line to arrive here at time t prime. That's because its length is this distance divided by the time interval. So that's why we think of this as a velocity vector. And in fact, we call it the average velocity. What we're now going to do is we're going to look at smaller and smaller time intervals. That is, we're going to take t prime closer and closer to t. So this point gets closer and closer to here. This velocity vector gets closer and closer to what we think of as the instantaneous velocity at time t, which is in the tangent direction. So if we can give this expression some meaning when t prime equals t, we can sensibly use that as our definition of velocity at alpha t. Well, let's do that. Alpha t prime has coordinates f of t prime and g of t prime. So the first component is just this. And the second component, it's the same except with f replaced by g. And again we write one above the other to show that it's a free vector. So what I now must do is I must find some meaning for this and this expression when t prime equals t, and you might have guessed by now that derivatives are going to be involved. You see, if the functions f and g are differentiable at time t, then these expressions are just their chord slope functions evaluated at some time t prime not equal to t. And when t prime equals t, the value of the chord slope functions are just the values of the derivatives. So the velocity vector in terms of alpha has components df of t and dg of t. And in fact, this is how we define the derivative. We say that this velocity vector is the derivative of alpha, and we denote it by d alpha of t. Well, anyway, this equation, or this simplified form, gives us the required connection between v and alpha. That is, the velocity in terms of the flow field v is equal to the velocity in terms of alpha. Well, now that we've got this connection, comes the crucial question of existence. That is, if to start off we only know the flow field v, can we be sure there exists flow functions alpha satisfying this equation? That is, do flow functions exist? Chris?
Well, that depends on which flow field you start with. But the answer for a large class of flow fields is yes, flow functions do exist. You can see this is plausible if I give you a physical analogy. Let's suppose that this flow field represents the velocities in a flow of water. In other words, the water flows past any point xy with a velocity which is precisely v at xy. Now consider a specific point P, and imagine yourself dropping a particle into the water at that point and starting a stopwatch. Then the particle will move off with a velocity equal to the flow vector at P, and you'd expect its subsequent motion to be predetermined along a flow line. That is, you'd expect its motion could be described by a unique function alpha, where alpha is such that the velocity of the particle expressed in terms of alpha is equal to the known flow velocity, with alpha at time 0 equal to p. By the way, you have to think of this part of the motion down here as happening in the past, because it corresponds to negative values of t. But anyway, this water flow analogy does make it plausible that flow functions alpha could exist. But let's write the existence question formally to make it clear. Given a flow field and a proposed starting point P, can we find a function alpha which is a genuine flow function and which does start at P? And the answer is yes, at least for a large class of flow fields. You'll learn more about that class in this unit, but the proof of the theorem won't come until later in the course. Anyway, the class contains all the flow fields you'll meet in the course, including the one Peter showed us earlier. So now let's look at that one and see how to find a flow function for it.
Well, remember that this is our flow field, and we're looking for a flow function starting at the point P, whose coordinates I've called R and S, and satisfying this equation. Well, V at the point xy has components 1 and the y coordinate. So over here we're going to want 1 and g of t. So we're going to need to satisfy these two differential equations, that is df of t equals 1 and dg of t equals g of t. And of course we want f of 0 equals r and g of 0 equals s. Well, these functions do just that. T plus r and s times e to the power t satisfy these conditions because when we differentiate this, we get 1, and when we differentiate this function g, we get itself as required. And if we set t equal to 0, here we get r, and here we get s, again as required. Well, notice that r and s could be any real numbers, so we can find a flow function beginning at any point of the plane. For instance, we can find one starting here at the point 0, 1. Of course, we'll get a different flow line, but we can very easily write down an equation for the flow function because here r equals 0, s equals 1, so this becomes t, and this becomes e to the power t, and I've written it down here. In the second part of the program, we're going to use this flow function to study the function e to the power t itself. But first of all, there's a very important theoretical point that I've missed out, and that is the uniqueness of flow functions. You see, here we have one flow function starting at the point 0, 1, but are there any others?
Well, the answer is no. That's a part of our theorem which I left out earlier to simplify things. But it's a most important part of the theorem. The full theorem actually gives not only the existence of a flow function alpha, but also its uniqueness. There's one and only one function alpha satisfying the flow conditions. Another result we'll need later is an important consequence of the uniqueness part of the theorem. To illustrate the result, let's go back to this water flow analogy. Suppose I've dropped my particle in at time 0, and alpha gives the flow line. And now suppose the particle passes a second person further along the flow line, say after time t equals c. And that he starts his stopwatch then. So his flow function certainly has to be different for alpha because it starts at this different point here. And it turns out that the function beta, defined like this, does the job. It starts at the correct point because putting t equals 0 in here gives alpha of c, and it is a flow function. Now, to show this, we have to show that the velocity in terms of beta equals the given flow vector v at beta of t. Now, to differentiate beta, notice it's a composite function. T maps to t plus c, followed by alpha. So we have to use the composite rule, which gives us d alpha of t plus c times the derivative of t plus c, which is 1. So it's just this. And we know that that's equal to v at alpha of t plus c because this equality holds for all values of t. And finally, this last equality here holds because alpha of t plus c is equal to beta of t. So beta is a flow function, and by the uniqueness part of our theorem, it's the only flow function starting at alpha of c. And this is the last result we'll need for our study of e to the power t.
We're going to use the same flow field as before, and the specific flow function beginning at the point 0, 1, which we said was given by this expression because the derivative of e to the power t was just itself as required. Well, how do we know that? We proved that in our last program, but to do so, we used several assumptions about e to the t that were made earlier in the course but never completely proved. You see, we never completed the proof that e to the t was defined for all irrational t, and we certainly didn't prove that it was differentiable. Well, in the remainder of the program, we're going to put all that right. We're going to use our flow function theorem to clinch the existence of a genuine function with all the properties we've been assuming for e to the power t. Well, our theorem tells us there exist unique functions f and g satisfying these differential equations, and so t is still okay, but now we can't put g of t equal to e to the power t, because that's what we're trying to show exists. So let's just call it capital E of t. Now our theorem tells us that capital E is the unique function satisfying these conditions. And in fact, it's this function, capital E, that we're going to prove satisfies all the properties we've been assuming for e to the power t. Well, two of these properties are continuity and differentiability.
Well, they're easy. First of all, differentiability is implicit in our theorem. The theorem says the derivative of alpha at t equals v at alpha of t. So it's certainly saying that alpha is differentiable.
And so by definition, alpha's coordinate functions are differentiable. And so capital E is differentiable. Well, what about continuity? Since differentiability implies continuity, that's okay too. Well, what other results have we been assuming? A really fundamental result is the law of indices. So we're going to need an equivalent form for capital E. And here it is. And it's the proof of this that's going to take up the main part of the rest of the program. We're going to prove the law by considering the flow function which starts at the point alpha c. And we're going to find two forms of the function. One form we know already from our last general result. And this gives us the left-hand side of our equation. And the right-hand side will come from an alternative form of the same flow function. To get that alternative form, we're going to apply a transformation of the plane, which takes the point 0, 1 to the point c, E of c. And the transformation I use is the composite I used in the last program. First we translate to the right through a distance c, and then we stretch in the y direction by a factor E of c. So the point 0, 1 first translates to c1, and then when we stretch in the y direction, we get to here, c, E of c. And when we apply this transformation to the path of alpha, first of all we get this dotted curve, and then when we stretch in the y direction, what we get is the path of this function. Why is that? That's because when we translate to the right, t becomes t plus c, and when we stretch in the y direction, this is left unchanged. Now when we translate to the right, the y coordinate remains unchanged, but when we stretch in the y direction, this gets multiplied by the factor E of c. Now our result will follow if we can show that gamma is an alternative representation of beta, because then their second coordinates will be equal as required. In fact, we're going to do rather more. We're going to show that gamma is a flow function beginning at the same point as beta, and since the flow function starting at this point is unique, it'll equal beta, and again the result will follow. Well, to show that gamma starts at the right point is easy. When t equals 0, this is c, and then because E of 0 equals 1, we just get E of c here. Now, to show it's a flow function, we have to show that this is equal to this. Now, the first component of the gamma t is just equal to 1, because when we differentiate this, we get 1. And the second component, well, that's just equal to this y coordinate of gamma t, because when we differentiate, this constant remains unchanged, and the derivative of E of t, well, that's just E of t again. So d gamma of t has components 1 and the y coordinate of gamma t. So now this equality follows because if you remember, v at the point xy has components 1 and the y coordinate. So we have shown that gamma is a flow function beginning at the same point as beta, so it's equal to beta, and we've proved our result. Well, it's this result that's going to enable us to show that capital E of t is equal to e to the power t. Because you see, the corresponding law of indices is what we use to actually calculate values of e to the power t. So if we go through the same process for capital E of t, we'll eventually be able to show that capital E of t is equal to e to the power t.
process actually involves finding the values of capital E in terms of its value at t equals 1. If we call this value A, then we'll be able to prove that E of t equals a to the power t. And eventually we'll show that A is this number E. Okay. To prove this, we first prove it for t, a positive integer capital N. And then for t, the reciprocal of a positive integer. And from there it can be proved for t rational, and finally for all real t. It's the standard proof you've met in the past, so I'll just briefly go through the steps. For t, a positive integer, capital N, we express n as the sum of n ones. Then the law of indices tells us that this is e of 1 times itself n times, a times itself n times, so that's a to the n. Then down here, we write 1 as the sum of m 1 over m's. Then the law of indices tells us that this is e of 1 over m times itself m times, so that a equals this. Then, taking mth roots, we get that e of 1 over m is the mth root of a to the 1 over m. Well, as you know, we can extend this to cover all rationals n over m by similar methods. But what about irrational values of t? Well, remember the rational rule, which says that if two functions agree on the rationals and they're both continuous everywhere, then they must agree everywhere. Well, we know capital E is continuous everywhere, but what about the function t maps to a to the t? Well, remember in a previous unit that for any number a, once we got a to the t for rational t, the way we extended it for irrational t indicated that the function t maps to a to the t is continuous. So both functions are continuous everywhere and they agree on the rationals. Therefore, the rational rule ensures that they agree everywhere. So that's proved that e of t is some number to the power t. Finally, it remains to show that a equals the number e. Well, how did we define the number e in the first place? If we call e to the t g of t, then the way we defined e was to assume that all exponential functions are differentiable at 0, and that e is that number whose exponential function has slope 1 at 0. But we've just proved that capital E is an exponential function, and we know that it's differentiable. As for its slope at 0, well, it satisfies these two conditions. That's how we defined it. So dE of 0 equals E of 0, which is 1. So a to the t is an exponential function whose slope at 0 equals 1, just like g. Therefore, a must equal e. And so, capital E of t equals small e to the power t.
So that does it. We've finally shown the existence of a unique function satisfying all the properties we've been assuming for e to the power t. So let's just summarise how we did it. Our theorem told us that given a suitable flow field, there's a unique flow function starting at each point. In our particular case, the second coordinate gave us the unique function capital E satisfying these conditions, from which we were able to deduce the law of indices and eventually show that capital E of t was just equal to e to the power t. So what we've eventually done is we've defined e to the power t properly in terms of capital E, where capital E is the unique function satisfying these conditions.